So hi, everyone. I'm Tom Talpe. I'm architect in the file server team. I'm responsible for a bunch of the protocols in the SMB3 area, but in particular, in this context here, I'm responsible for the documentation that we produce for SMB. The documentation is a really key aspect of our interoperability story, if you will, and of our partner engagements, our ecosystem that we built, right? Microsoft has built over the past 8 years, I forget how many years it is now, a really high quality set of protocol documents, right? They are extremely complete, thorough, written very carefully, tested, right? We test every document against the implementation. We describe the behavior of many versions of Windows all the way back to NT4 in the case of the file sharing set. And they are very, very comprehensive, complete, thorough documents. And so when we embarked on the SMB 2.2 at the time, I'll talk about that, protocol effort, we were rethinking the way the SMB2 protocol could be used for application server deployment. The protocol documents were sort of the first outgoing message that we would provide, and we provided documentation very early on. The first SMB3, or SMB 2.2 at the time, documents were published back in September of last year, just before SDC. And we've revved them 5 or 6 times since then. We're getting ready to publish them officially for the Windows 8 release, which is still a date TBD in the future. But the official publication, that big preliminary watermark, will vanish from those documents, and they'll become official documents. So anyway, what I want to talk about today, this is a reprise of a talk that I gave at Samba XP last month in Göttingen, Germany, is the feature map of SMB 3.0, all the things you see in the document that are tagged with SMB 3.0, and how that feature map maps to the things that SMB 3 is intended to do in the field, in the market, in the interop world, if you will. As I said, SMB3 is about capturing enterprise applications. It's about exposing cluster continuous availability behavior on the part of the file server, for instance. And so the question is, well, I see a 600-page document. What pieces of that document are relevant to this piece of the enterprise story, right? And so my goal in this presentation is to kind of deconstruct the protocol a little bit. I'm going to stay at a pretty high level. I'm not going to go too deep. But that deconstruction, I hope, will be interesting and important to you as a way of thinking about the protocol as a set of features that are really optional. Almost all the features in SMB3 are optional. The client chooses to do them. The server chooses to implement them. And if the two agree on desire to use them and ability to support them, they'll be used. But you can actually have an SMB3 client and server that support almost nothing in SMB3, almost none of the interesting features of SMB3. It's kind of a dirty little secret, perhaps, that we'd rather nobody comes out with. Nobody ships such a thing. But the reality is that there's a very smooth and clean upgrade path from the earlier versions of SMB2 to SMB3. So I want to try to just show it to you a little bit. So first off, I want to give you a status update. This status update is getting a little bit old. You've probably seen it before. It happened back in April, but only about 2 months ago. So if you blink, you might have missed it. I want to list the SMB3 features, and then I want to map them to the protocol and maybe motivate a phased approach. So at a high level, this is the SMB3 feature set. Overall, we say remote file storage for server applications, right? It's about server apps. These are things that were never supported or which never chose to support SMB file service or storage. There were various reasons for that, but primary among them were the availability features that SMB did or did not provide, right? These enterprise apps are continuously available apps. They can tolerate no more than a few seconds of outage. When they do have an outage, they need to come back quickly with all their state intact. And so the features of SMB2 were a bit of a challenge for them. And that was a main motivator as we developed the feature set of SMB3, or what came to be known as SMB3. And so the features that you see in bullets are, roughly speaking, at some high level, the features that SMB3 supports. Transparent failover to allow clients to move from server to server. SMB scale out to allow highly scaled servers, multiple clustered servers, for instance. SMB direct, the SMB over RDMA story, which enables an incredible performance story between client and server. SMB multi-channel, which works with SMB direct and with TCP to support multi-pathing for both redundancy, availability, and performance. Snapshotting for SMB file shares. We support the full VSS facility remotely now for an SMB file share. SMB directory leasing, improving the performance of clients who want to cache directories as well as files. Actually can own the directory with a lease and manage it without contacting the server at all. SMB encryption to allow deployment of SMB in enterprise environments where data integrity and data privacy are extremely important. It can also be deployed on a WAN. Perhaps you could deploy SMB even more broadly with encryption. And Branch Cache v2, SMB already supports Branch Cache v1, but Branch Cache v2 came along in Win8, and SMB supports Branch Cache v2. Primary feature there is variable block size, variable caching atoms. So SMB 3.0. SMB 2.2 is now SMB 3.0. We have, if I can get my mouse here, we made a presentation a couple months ago. Here we are. And it was blogged about, and the blog URL is in the presentation. But basically, the SMB 2.2 was our story until a couple months ago as the next generation of SMB, right? And we were getting incredible traction on it. As we got incredible traction on it, we realized that there was an incredible interest in the industry for SMB 2.2. And yet SMB 2.2, was a new thing, but it didn't really sound all that new. It didn't call the attention to SMB 2 that we actually believed the industry was demanding, as it turns out. And so we made a decision to rebrand SMB 2. We made a decision to call it by some new handle, right? That this new release that we're doing with Windows 8 is now special. And after a long and tortured process, the decision was to call it SMB 3. So 3 it is, and this was announced a couple months ago. There is no functional change across the boundary from 2.2 to 3.0, except for the dialect number, which is now negotiated explicitly as 0x300. Everything else stayed exactly the same. There was a slight change to the validate, negotiate FSCTL that clients and servers use to prevent man-in-the-middle attacks. But everything else, basically, we just crossed out 2.2 and wrote in 3.0. So this announcement was a couple months ago, 19th of April. And I put it up there so that you will understand that that's the foundation of what I'm talking about here. It's a rebranding because it's truly a major release and to specifically highlight the new server application support. And we hope that our partners, our development partners in the industry agree that this was the right thing to do. It is a major way to call attention to SMB2 and to really give it the attention, the recognition that it deserves because of the feature set. The preview is always available at this wild and wacky URL. You can get to this from the Microsoft.com/protocols site very easily. The preview has been updated just actually about a week and a half ago with nearly final content. There's still maintenance going on. There will always be maintenance going on. This document's never finished. But the preview's been available for a couple weeks now. And the SMB3 previews, as I said, have been available since September. So this isn't new. To get to actually implementing it, supporting 3.0, it's a superset. It's strictly a superset of SMB2.x. All the new behaviors are optional, except for one. They're client initiated optionally. The client chooses to do them. And they're server acknowledged or server supported optionally. The server can can decline to support them. Everything is negotiated, almost everything. And clients initiate the use of the features. So there's sort of two things that kick it off. First, the client's ability to support the feature. And second, and perhaps more important, the interest in the application of requesting the feature. Some of these things will happen automatically, right? But other times the server, and this is particularly true of the Microsoft server applications, will have specific requirements and will make specific requests of the client saying, connect with this protocol, or, if you don't get this protocol, tell me. Make sure that it's a continuously available server if that's the way the client needs to be deployed. Or make sure that, various features below are present. So it's really the whole stack that's participating in SMB 3.0, all the way up to the application level. A bit of a broadening of the agenda. The decision to support those features is therefore first and foremost an application question. Does the application require it? Does the application prefer it? So here's the dialect negotiation. This is our new picture, complete with our little mascot, who will survive for a little while longer before he disappears from the document. But you might remember him from the SDC presentation, Bigger, Faster, Scalier. And he's our mascot. He's bigger, he's faster, and he's a whole lot scalier for SMB 3.0. But basically, this is the same state diagram you know and love. It's just been turned a little bit on its side. Oops. It comes in up here with nothing. And it has various ways. These 6 different arrows are various different ways to negotiate the protocol. There's the old string version, the SMB negotiate, that has 2 different flavors, right, to leave SMB1 and move to SMB2. You can either directly go to 2.002, the Vista version, or the wildcard version to SMB2 any. And followed by the various SMB2 flavor negotiations. And there are basically 3 direct and 3 indirect versions. But they all terminate in one of these 3 versions of SMB. 2.2, the Vista flavor, 2.1, 2.02, I'm sorry, the Vista flavor, 2.1, the Windows 7 flavor, and 3.0, the Windows 8 flavor. And down here at the bottom, this is what happens when it fails. You drop out the bottom, and you probably wind up at SMB1, right? If you don't successfully negotiate these, the state diagram dumps you to SMB1. Chris?
A question on the top there at the start. Does that start encompass both SMB1 and SMB2 negotiate protocols? Because they're different formats.
They are very different formats, right. and that's what this SMB string version is. Right. That's so the SMB1 negotiation, and this hex version is the SMB2 negotiation.
Because most implementations will look at the format of the first packet and say, oh, that's an SMB1. So you'll probably split that start state before you even get to it, is what I'm thinking.
It's the choice of the client which one to offer first. The Microsoft client will typically start with an unknown server. This is in the doc. Will typically start with the string version SMB1 negotiation because that's the most common one. Okay. And if it's 2.x capable, it will offer the 2.question in all likelihood, right? And so it'll go straight to this state, right? And skip the SMB1 negotiation altogether. Other clients might not. They might come in with SMB landman, 0.12 and go straight to SMB1 and never even bother with the SMB2 code path. It's pretty much the client's choice. Okay. The Windows client will, in an unknown server, always do this first. Once it knows that the server is SMB2 capable, it'll actually move directly to this and save itself a round trip on new sessions. Okay, it's mentioned in a behavior note.
Good. Thanks.
So, question. So
yeah.
when the server responds with, if server is SMB2, and against the wildcard it responds with 2FF, right?
If the server supports SMB2, yes, you can wildcard the first negotiation step to 2FF, absolutely. What you'd do is you'd perform one of these SMB2.question strings. You'd basically probe, you'd send an array of strings, basically, that says all the dialects you're willing to support as a client. The server will recognize 2.question to move directly to this state and say, okay, we're doing SMB2. At that point, no further SMB1 messages are exchanged on the connection. and it moves directly to one of these SMB2 style negotiations. It's kind of a two-step negotiation. This is an SMB1 string version. That's an SMB2 hex version. Or it can go directly to that if it started with SMB2. The state didn't change. It's just that we added this new circle down here in the bottom, basically.
Was the purpose of the two-state negotiation to get those extra fields in from the client on the SMB2 negotiate packet, like the client GUID?
Was the purpose, I'm sorry, I'm repeating the question, was the purpose of the two-step negotiation to exchange things like the client GUID? Not exactly. The two-step negotiation was there to basically allow compatibility with down-level SMB1 servers. This negotiation was developed way back in 2006 for Vista, right?
No, but to clarify, it is true that for Windows 7, we needed to get client capabilities as part of Negotiate. So if you do a wildcard negotiation like an SMB1 class, you don't get the SMB2 capabilities. So it was both, and then question mark also prevented us from loading the SMB1 multi-protocol negotiate with 5 or 6 SMB2 strings as well over time. So there was a bit of both. So.
Okay.
Just curious.
Protocol changes from 2.1. I'm just going to try to summarize them. David's going to have a presentation later today. David Cruzy, who's speaking from the back here, is going to have a presentation later today with more detail. But I'll just give a summary. The document is always the official source, putting on my documentation hat. Unless, of course, there's a bug in the document, in which case file one, please, right? These documents are forever changing. They're forever being tested. They'll always and forever adapt. That's not to say we don't want them to be perfect. It's just that, in a 648-page document, I think it's up to today, we acknowledge there's always going to be something to do. Negotiation changes. There's a new dialect number, 0x300. The dialect array typically contains 3 entries, not 2. The dialect array is present in the SMB2 flavor negotiate. It used to be that a modern Windows server would send two versions, right? 2.1 and 2.002. Now it's sending 3 versions, typically. Client capabilities have been added to the negotiate request, as we just mentioned. These are basically flags in an existing field that was reserved. The global capabilities of the client are pushed to the server before the client has even determined what the server supports. And the server capabilities, the server used to have all of these things, but we've added 4 new ones: multi-channel, persistent handle, direct releasing, and encryption. So the server capabilities come back in the negotiate response. So after the negotiate exchange, the client and server have exchanged a full set of capability bits, and they have a pretty good idea of what each one supports. So this is kind of the first step in optional behavior. If you as a client don't want any of these things, just don't turn them on in the negotiate. The server knows you don't want them. The server basically is prepared to deal with you in whatever mode you're willing to support. And of course, in SMB 2002 and 2.1, these bits weren't on in the first place. So you're basically getting down-level behavior when you turn off all those bits. But normally we would expect a full function 3.0 client to set almost all these bits. They're optional, but we'd expect you. So the negotiation request, basically only these 2 fields really changed. The capabilities, which are used in both client and server. Yeah, Jeff.
So I guess the server just doesn't look at those flags unless you set the dialect to 3.
The flags are only valid if the dialect is 3.
Okay.
Yeah, if you set them, well, they won't have any meaning in 2.x.
Trying to figure out why you have to do both, but that makes sense. Okay.
Right. So this is just the definition of the flags, and then the value with the various dialect numbers, 202, 210, and 300. So those were the only changes in the negotiate request. In the negotiate response, just the flags. These flags were already here, first 3, and these 4 flags are the new ones for SMB3. And you can see how they say right there, this flag is only valid for, this flag is only valid for, et cetera, et cetera.
Although you just still have the prefix SMB2.
We do. We decided early on in this process that we were only rebranding the protocol. We were not changing the protocol. And we did not want to, for instance, publish two documents which were largely identical, one called SMB3 and one called SMB2. We felt that would serve nothing, nobody. It would just drive us all crazy. We would have two fundamentally identical documents. So we have intentionally not changed the names of the fields, not changed the base name of the document, not changed the base handle by which we refer to the protocol. We'll refer to SMB3 and SMB2 interchangeably when we're talking about the broad spectrum of support. But we'll talk, when we say SMB3, you know, we're specifically talking about a feature that's present in SMB 2.2/SMB3.0. So you'll see SMB2 everywhere. You'll rarely see the string SMB3 in a protocol. Over time, who knows? Maybe that'll change. But for now, one document, one protocol, SMB2, 3 dialects. Chris?
There is precedent for that because in the OS2 days, the SMB flavor was called LAN Manager.
Right.
And they had multiple different versions. There was 1.0, 1.1, 2.0, 2.1.
Flavor upon flavor. Right.
I'm not loud enough for you? Oh, they're recording. Yeah, I was just saying there was precedent with the LAN Manager dialects back in the OS2 days.
Yeah. Well, honestly, we were trying not to go back quite that far in time, but the precedent is well appreciated.
But the history is so important. And the number of things that are in SMB2 that really do go back to the OS2 days that I can point to.
I know.
Yeah.
I know.
And Daryl, you really want to stop me from recording the rest of my... You're going to take this away from me.
Thank you, Chris. Chris, what you didn't see is what the dinosaur guy is chasing off the screen.
Yeah, right.
So session setup. Session setup includes a single new flag called session flag binding. It's in support of multi-channel. Basically, you will create a session on one connection, and multi-channel allows you to join that session from one or more other connections. And so this binding flag is the flag that you use when you're connecting those auxiliary sessions. The request must be signed. That's one interesting little thing. This is one place where signing starts to sneak in, that obviously you don't want arbitrary second connections joining your session without some proof. And so signing is used for that. The session setup response includes a new flag, and that's session flag encrypt data. This is the global encryption flag that says that the server requires or recommends that you use encryption on this connection. Talk about that in a second. So these were the only two real changes to the session setup: request on the top, response on the bottom, with those two flags. So pretty simple change there. Header changes. The fundamental SMB2 header, the thing that precedes all the operations. There's a new channel sequence in the header, both for sync and async. Channel sequence is used if multi-channel or persistent handles are in use, and it's used to basically enforce sequencing and fencing on replay operations. The channel sequence is a small integer, I'll show you in a sec, and it's present in every message when those attributes are in use on the session. There's a new replay operation flag in the header and a create GUID identifier in the open, plus various per open state tracking, et cetera, that you can find. This is behavior, not protocol, in the document. There's a new status code that can come back for a replay operation called status file not available, that flags that replay was detected, and further recovery is required before the replay can be resolved. All this stuff is in the doc. It's like, once again, it's not my goal to go into detail on these right now. So there's the field. It used to be reserved, half status. The request changes it to that channel sequence meaning. The response always has status in it. So channel sequence only appears on the request. Tree Connect. The Tree Connect operation changed to add 2 share attributes. Hash v2, saying that the share to which you've connected supports v2 hash protocol, as well as share flag encrypt data. This is similar to that session flag, but it's scoped to just the share. Normally, in fact, this is the normal case where the share has an attribute that says encrypt this share. It contains, high business impact data, right? So encrypt everything that comes and goes to this share. So it's interesting. You can actually get a connection that is a mix of encrypted and unencrypted data, right? Because you could have a connection with multiple sessions that access multiple shares, only some of which are encrypted. So the requests on any given connection will exhibit a mix of behaviors potentially. Now, of course, not if that whole session flag was true. Then all your shares will have the same behavior. But I think that's an interesting feature of this protocol that you've got to be aware of when you're tracing, for instance. You'll suddenly see a message that's just a blob.
Session encryption basically overrides tree-level encryption.
Overrides, yeah, it's an OR, right? If session encryption is in force, all messages on the session must be encrypted. Yeah. Tree Connect response adds server capabilities. There's a couple of these things that are server capabilities which appear depending on what share has been accessed. Continuous availability, scale out, and cluster are these 3 attributes of the share. They interact in funny ways. I'd encourage you to look at the document about some of these things. They mean slightly different things. They indicate slightly different features, if you will, that the server implements. And the way some of them require the client to perform certain additional operations. Some of them allow the client to perform certain additional operations. Like in one case, one of them says that the witness protocol is available for enhanced availability. The Tree Connect response, actually one of these flags has been renamed. This SHI 1005 has actually changed to SMB2 share flag now. Only in the most recent preview, so you might want to have a heads up on that. And they're the meaning of the flags. So you can see a little brief text. But once again, all these flags will be tagged with the statement, only valid for the 3.0 guide. Create. There's a 4 new. Create context in the create requests. Request least v2, handle request v2, handle reconnect v2. Those 3 things are basically additional enhancements over the existing create contexts. And a totally new create context called the app instance ID. That's used for application failover. It allows an application to identify itself to the server, not just the client, the whole end-to-end application picture. This allows for failover. Create can request a lease on directories. So that's a new behavior, if you will, that the protocol enables. The create response includes a reparse point flag as the create is responded to, the reparse point status is immediately reflected. The create response context, only 2 of them here, right? Lease v2 and handle response v2. The other 2 have either no response or they filter, their behavior filters into existing responses. Read and write channel info is an old field with a new meaning in SMB3 for RDMA, and read and write don't change in any other way, only for RDMA. You may have seen the RDMA presentation at SDC. This is basically the same information. The channel field, read channel info, and write channel info offsets and lengths are basically take on a meaning now in SMB3 when RDMA is in force. Normally that channel field was reserved and must be 0. That's the old behavior, the TCP behavior, if you will. IOCTL and FSCTL, there are 2 new SMB-specific IOCTLs. These are originated from the client itself, not from the application above the client. FSCTL validate negotiate info protects against a man-in-the-middle negotiation downgrade. Right? You could intercept the negotiate request, chop off SMB2, and downgrade the client to SMB1 and lose all the features. Right? So the validate negotiate info is an end-to-end negotiate that's responded to by the server. Its goal is to validate that there was no downgrade of the dialect or security mode capabilities in server IP. Right? All these things are verifiable using this FSCTL. So it basically repeats the negotiate process on the signed and sealed end-to-end channel. And a signed response, even an error, can be used to validate that result end-to-end. Because a signed response had to originate from the server we were authenticated with, right? So this is performed by default by Windows 8 clients, even on down-level connections. And they depend on this signed response behavior to figure out that they really truly believe that this was not a 3.0 capable server that somebody downgraded, an evil man in the middle downgraded. So you'll see this a lot. All Windows 8 clients will originate this shortly after the tree connect.
And that works over SMB1 because it has to, because of the downgrade, right?
It doesn't work over SMB1. It's only issued on an SMB2 connection.
So this confuses me. The purpose of this is to say, were you actually capable of doing SMB2, but I got downgraded? And
Yeah, well, if the maybe I misunderstood your question. If you have an SMB 3.0 capable client,
right,
who attempted an SMB2 flavor connection in some way,
Three,
offered 3.0 in
Right.
his negotiate request,
Mhm.
then he will always issue this. That's true, even if he winds up in SMB1.
right, that's what I was getting to.
Right.
Yes.
But if he went in with the intention of SMB1, if you disabled
Oh
SMB2,
yeah, then that doesn't
Right.
matter.
you wouldn't see this from any other client.
But the client is, even if the server says I can only do SMB1, the client's going to issue this.
Right, the client can't believe it until it knows end to end that the server was the one who said that. Right?
And then what it'll get back from the server is an error if the server really doesn't.
Well, it would be a signing error if it was an error, right? So the client will get back an unsigned error and it'll go, phooey, I don't believe that for a minute, right? It's the signing, not the error, that spooked the client.
Tom?
Yes.
SMB1 doesn't support unsolicited signed requests. Sorry.
Right.
SMB1 doesn't support unsolicited signed requests, so we actually won't issue it across SMB1 because even our own servers wouldn't sign it. So
When
to prevent
signing-
downgrade to SMB1, you actually disable SMB1 on the client. There's no way we could verify if you fall down to SMB1, especially the older dialects.
That's what I'm getting at, yeah.
So,
I don't think there is a way to.
It's probably downgrade from 3.0 to 2.0.
right,
There is a blog on this,
yeah.
Okay.
and it recommends this.
But
Yeah.
again, if it's a man in the middle server that downgrades the client's request to SMB1 so that it can attack, there's no real way for the client, even with this capability, there's no way for the client to verify with the server that it got what the server actually offers. Is that what, I think that's what I'm hearing from the discussion.
I'm trying to be careful in the response to answer it in Windows behavior terms or in protocol behavior terms.
This is in my presentation too, if we want to talk about it more at 10
Okay.
o'clock.
Why don't let David do it? I think that'll give you the better answer. Honestly, the protocol, I don't know, this is my occasional, not so much rant, but the documents are required to describe the behavior of Windows, right? They aren't allowed to sort of elaborate on the abstract properties of a protocol. First and foremost, and what we're required to do is describe what Windows actually does. So the possibilities may be endless, but the document won't speculate in these kinds of cases. Query network interface info is another new one that you'll see clients issuing when they do detect SMB 3.0 end-to-end. It's used for multi-channel discovery, including RDMA. Basically, the client will connect over one TCP link first, always. Once it negotiates 3.0, it will query for other possibilities. The server will enumerate other network interfaces. The client will enumerate its network interfaces, perform various client-dependent routing lookups, and decide, hey, I could actually connect to this server multiple times. Maybe from one connection to multiple server interfaces, maybe from multiple client connections to multiple server interfaces, or maybe even change technology of the interface. So that's how the client discovers server capabilities. The real big advantage of this approach is that there's no configuration required. The client connects via the protocol that it expects, TCP, and then it discovers other protocols and can begin to use them if they're available. So that's pretty cool. There's an enhancement to the DFS GET referrals that includes the DFS site name. You can read about that in MS-DFS-C as well as in SMB2. And there are a bunch of new FSCTLs that are handled by the file system that you'll find in MSFSA and MSFSCC. Offload reading and writing and trim support, for instance, are some of the more interesting ones that are used by the virtualization managers. They're simply passed through by SMB. There's a thin layer of checking that there's a validity in the requests, but primarily they're handled by the storage system, just like all the other types of file I/O requests. So there's the validate, negotiate info. The request is the same as almost the same as the response in the new version. If you looked at SMB 2.2 before, there was actually no response to the negotiate info. There was only a status. Now there's actually a structure that parrots these things back. But the four elements, the capabilities, the GUID, the security mode, and the dialect, this is the response, the new one. In the request, this is actually an array of the dialects originally requested. Here's the network interface info. The IF index is a local number. The capability is that set of bits. There's only 2 of them. Reserved used to be the RSS queue length, but that's not used, so we've made it reserved. Link speed is the speed of the link. So a combination of the capability and the speed pretty much tells the client what type of device it is. And the socket or storage is the address of the interface. File system control, this is similar to the FSCTLs. There's a new sector info query that you'll see on the wire. We actually recently corrected an omission in the document. We forgot to list that one. Almost all these things are passed through to the file system. Encryption and signing, one more new thing. There's a new signing algorithm, AES CMAC 128. It's described in IETF RFC 4493. It's used for all SMB 3.0 signing now. It's more efficient than HMAC SHA-256, the older version, and it's compatible with encryption. It uses the same fundamental algorithms as encryption when it's used. It's supported by the processor, by modern processors. Modern Intel and AMD processors support this in instructions. And so it's way more efficient. I think David talks about this with a little bit of more detail. So. There's a per-session signing key, as well as a per-session encryption and decryption key. So there are actually 3 keys on a given session. Encryption is now supported. This is a first and a huge major change for SMB. It uses AES 128 CCM, similar to the hashing function up there. It can be enabled per share or for the whole server. It's optional, right? Signing is not. Optional is. It encrypts individual requests on single connection. So as I say, this can lead to very interesting packet traces when you have a share that's encrypted. The transform header is used for the encryption. And basically, there's a transform header prepended to the existing SMB request that contains the encryption information, the information about how the message was encrypted. And then the rest of the message is the encrypted SMB payload that would have been sent in the clear previously. Encryption is extensible to multiple algorithms, but only AES 128 CCM is currently supported. It's strictly speaking not negotiated. There's a token, a little number that appears in the field, right? 0x001, which goes in there in the encryption algorithm down here, that short word. But it's not strictly encrypted, not strictly negotiated. Whoopsie. I'd call it advertised rather than negotiated currently. But we may add new encryption flavors in the future. And miscellaneous, the lease break V2 adds an epic field. There's a new format of the lease break for when it's a V2 flavor lease that adds an epic used for sorting out the leasing behaviors. Multi-channel has a many-to-many association. So it's interesting. Now you can have multiple sessions on a channel and multiple channels on a session. So you can have all kinds of strange associations of TCP connections with sessions. From that, I just want to spin through the feature mapping. That's Captain Midnight. It's the Captain Midnight decoder ring that you spin to figure out what's going on.
Biggles?
I'm sorry?
It's not Biggles?
That's Captain Midnight.
Okay.
He came as a little picture that you tucked into the decoder batch. Pickles? Anyway, the question is, with all those changes, right, do I have to implement them all? How do I approach that list of protocol changes to figure out what to actually do as a developer? Can I do a staged approach? I want to try to motivate various ways of thinking to accomplish a staged approach. High-level SMB features from the blog. I'm just going to quote a paragraph from the blog and a suggestion, serving suggestion. Many of the features are specifically designed for server applications, blah, blah, blah. It's important always to answer these requirements individually. We're considering in the SMB2 space, primarily in the testing and exercising space, defining application profiles, right? The sort of things that we would expect an application to issue and the things that it's going to expect will behave in a certain way. We don't have those as part of the protocol and probably won't for some time, but they're fairly easy to identify once you think about a specific application. And so I encourage you to think about not just your client in general, but the application that client is going to service. Scale out is a really important feature for Windows, a Windows server, and it may well be an important feature for other servers as they appear in the market. But when we say we want to scale share bandwidth by adding cluster nodes, etc., in the Windows space, what we really mean are these three new features: continuous availability, new capabilities, continuous availability, scale out, and cluster attributes. They are sort of the keys that the server will expose to indicate that it supports these scale out features in various different ways. Clients and servers, when they access these types of servers, are going to expect persistent handles, right? That's kind of the whole key of continuous availability, that your handles don't die when you lose the connection to the server, that you can move to another server and reuse that same handle. Or you can get back to that same server and reuse that same handle, depending on how these bits have been exposed. And the third thing to consider is witness support. MSSWN is this RPC protocol that sits on the side of SMB. Witness is only used when the server indicates it's a cluster. And the witness support allows the client to more promptly know the status of all the nodes in the cluster. It allows for much, much faster failover. It avoids a timeout or a failure to detect this. The server can actually intentionally push clients around. You can load balance a server with witness. So whenever you're looking at scale out, you want to think about those obvious server flags, clients being able to handle, to deal with persistent handles, and witness support. Multi-channel. Okay, it's used for both availability and performance. But what do you do to implement? Well, actually, not that much. Server and client really just have to concern with the multi-channel capability attributes. And they need 2 or more equivalent interfaces. Windows will always use equivalent interfaces. It'll never try to merge a 1 gigabit channel with a 10 gigabit channel, for instance, or an RDMA channel with any other flavor of channel. It won't try to mix 2 speeds or 2 technologies. But this is behavior. There's a little bit of protocol in there, any place you see multi-channel, but it's primarily behavior. It's primarily the ability to listen on multiple connections, the ability to negotiate your session on alternate connections, etc. Every place you see multi-channel. pretty well focused. SMB Direct 3.0 over RDMA. You need multi-channel because that's how it detects the RDMA capability, both from the client to the server. And of course, you need RDMA-capable interfaces. There's a layered protocol called SMB Direct, described in the document MS-SMBD, which is required for this. The changes to the SMB2 protocol are really just that read and write and the multi-channel capability. This was done about a month ago, and these numbers have gone up substantially since then. I probably should have thrown in the new one. But with RDMA, some really phenomenal throughputs are capable. The 2-month-old number is just under 6 gigabytes per second on a single port. We're on our way to doubling that number, not quite. It's pretty phenomenal how fast it can go with how little overhead. If you look at these numbers here for bandwidth, you'll see there's a non-RDMA InfiniBand or Ethernet, an RDMA InfiniBand QDR, an RDMA InfiniBand FDR, and local. So this is basically running on the server. You can see that with FDR, we're achieving the same throughput with large IOs as we get locally. But look, the CPU is actually less. The client CPU, because it doesn't have to do the file system, is actually substantially less than we would have local. So this is a pretty good story, right? Take your storage off box and actually go faster, right? Have more CPU. On a IOP sensitive workload with 8 KB, you can see there's a limit we reach, right? It doesn't matter what the bandwidth of the technology is, we still reach a limit in the mid to low 300 Ks. But once again, look at the overhead, right? The overhead is slightly less, I guess. All right. But, you know, we're pushing only 73,000 IOPS with Ethernet. We're pushing 4 times, 5 times that much with RDMA. All these numbers are constantly changing as we keep working. So RDMA is pretty cool. Failover, transport failover, node fault tolerance. They're really just two. The scale out isn't as interesting here. It's all about the continuous availability and cluster attributes for the server. Of course, global cap persistent handles, the same as we saw in the scale out case. Witness, because of the cluster. And the client server application ID. That's the create context where the application identifies itself to the server and allows for faster failover, right? So there's sort of an end-to-end application to storage failover story as well as the SMB level story. This is probably the most complicated scenario, the one that requires the most moving parts. Volume shadow copy is kind of the opposite. There's absolutely no SMB3 requirements with this one. The volume shadow copy is an RPC protocol that sits on the side that creates, manages, and uses volume snapshots with exporting them as a share, basically. So, in effect, the FSR-VP protocol is a completely standalone protocol that manages snapshots, but then SMB3 comes in to actually access them, right? So you create them, they get this funny name with a GUID and a bunch of characters in them, and then you expose that with SMB3 to access it. So there's some coordination necessary. But this is an incredibly isolated protocol with really high value. There's a couple of new blogs coming out on this one soon. This one is pretty interesting from an SMB implementation perspective because of that line. Encryption, strongly recommend you try to support this because processors support it well. Client and server support of the new signing and encryption AES algorithms, server and client global cap encryption. This is a very focused thing, right? Basically, everything that was in the message is exactly the same, just a header goes on the front of it that only appears when it was negotiated. Encryption has real high value. Encryption works for RDMA as well as for TCP, but encryption does not protect the RDMA transferred payload because that goes on a totally separate hardware affiliated, hardware managed communications channel. So encryption works with everything. Has good value there. Directory leasing, you need a file system that supports directory leasing, obviously, and client and server support of the directory leasing capability. Once again, this is something that you'll answer on a server basis as well as on a client basis if it wants directory leasing, if it gets a benefit from directory leasing. Windows certainly does. But once again, fairly focused. You don't have to do all of SMB3 to do this. The whole ecosystem basically is what we're talking about here, right? It's all these partners who are implementing SMB3, all the interoperability story with Windows. The documentation and these Plugfests are our primary means of encouraging and enabling that ecosystem. We have the file sharing Plugfest once a year. We have the SDC Plugfest, a little broader scope in September down at the SNIA Storage Developers Conference. We are hosting additional Plugfests for all the other Microsoft technologies here and elsewhere through the year. And the documents are updated anywhere from once a quarter to, I don't know, once a month in the case of previews. So there's a constant flow of information around these things that we're really glad you're part of and that we hope you maintain your participation. You may also consider some of these backside things. Storage subsystem, offload, read and write, and trim. If your storage subsystem or your file system supports these things, they can be exposed by SMB. Or if your application wants to use them, they can be invoked remotely now. The file system enhanced leasing, both directory leasing as well as file leasing. FSCC operations, there's basically a long list of file system control codes supported by NTFS and Windows. Branch cache v1 and the new v2. DFS site awareness. This is used for, in the Windows world, for something called direct access, where a remote client can be steered to the DFS server that's nearest or best to serve his needs, no matter where he is in the global internet. So in summary, cross out the 2.2 and write in 3.0. It's still bigger, faster, and scalier. That's our T-shirt from last SDC. But change your view to SMB3. Oops.
You get new shirts?
I don't know. Got any suggestions for September?
A stencil.
You got to show up at the SNIA Plugfest in order to find out.
Been taking my shirts and making pillowcases out of them because I have too many of them.
Oh, yeah. I saw a guy. He did a website where he had my career in T-shirts. He took all his T-shirts that he'd gotten in his life and scanned them and put them on a web page. He started like as a summer camp counselor when he was 10 or something like that, and they just, he had hundreds of T-shirts on his page. It was the funniest thing. Anyway, any final questions? We're basically right on time here. Yeah.
How the persistent handles are stored?
How are the persistent handles stored? Well, there's no requirement in the protocol how they're stored. The semantics of the handle are the important thing, right? So they're stored in whatever way the server that implements them chooses to. The persistence is bounded in time in general, a number of the server's choosing. So the server can use, that value to manage how it does it. The client requests a time period, and the server grants it. So typical persistence times are relatively short, minutes. Could be hours, could be years. Okay, thank you.
Nice job.